Modern power systems are considered one of the largest systems created by the humankind. Over a century, they have evolved from small, isolated systems to a vastly interconnected grid composed by probably millions of elements such as generators, transformers, loads, lines, and many other components associated with communications, protection, and control. The generated power at the power plants is sent at the speed of light to the loads through the transmission lines, which act as the vessels of the system. The role of transmission lines is essential for a proper grid operation, and they must provide enough transportation capacity and must perform the power transportation task efficiently. Let's consider a span of this transmission line, which is the part delimited from one particular tower to an adjacent tower. Let's assume that the total length of this line is equal to n of these spans. When we send power through this line will offer opposition to this power flow, which is characterized by the series resistance R and the series reactance X of the line. This opposition will create a difference between the voltages at both ends of the line. Consider that P and Q are the active and reactive power at the receiving end, and assume that the voltage at the sending end, V1, is fixed. Then, the voltage difference from the sending to the receiving end can be approximately estimated by R times P over V2 plus X times Q over V2. Note that if we desire to increase the transmitted power, the voltage difference will increase, and consequently the voltage V2 is reduced. In short, the greater the transmitted power, the lower the voltage. This behavior of a transmission line is very similar to what occurs in the blood vessel system. The blood is pumped by the heart and sent through the vessels. As the blood is passing through a vessel, the blood pressure is reduced. For example, let's consider one artery. The pressure at the beginning is P1, and it is higher than the pressure at the end of the artery, P2. If the blood flow is represented by F, then the relationship between flow and pressure is given by pressure difference is equal to the artery resistance R times the blood flow. A low pressure is a critical factor in the body's health. Likewise, a low voltage is a critical factor in a power system operation. In one sense, the greater the blood flow, the lower the blood pressure. With the case of a transmission line, a low voltage will reduce the capability of the line to transmit power and put the system under risk of losing stability.